Good morning, sir.
So today we'll observe two. One is that ADC problem, and then we'll club the concept of the timer to programmable clock out. Okay, to generate the clock for the ADC, right? So we'll try for that. And so we'll be opening the Proteus. And then initially, I will show you some preliminaries on these. And then I have already hardwared that ADC project. So we'll be opening later on that and work on that. So we can go with new projects. And so we'll browse this path at the beginning, right? Then Proteus work. So we can name this ADC, DAC, and then T2 clock. Okay, let it be like that. And then within that, or we can do this one. So this is the path we'll be working on. ADC, DAC, T2 clock. Okay. Sorry, T2. Next, we need schematic. We don't need PSB. We need firmware. And then we'll be choosing that 5.2, this one, ASM, and next, finish. Okay. So this is already we have seen earlier. Now this one we have done. Now we need to find some of them. So I insisted you to use these crystal oscillators and the capacitor here, although the facility is there to change it on the microcontroller itself. But it will keep you reminding that in the hardware you have to actually work with that circuit. Okay. So we can take this ADC 0808 and so analog devices. Double click it, it will come here. Then DAC 0808. And so we can know this. Now we may need this pull-up register. So in this case, what we can do, we can go for register pack. Okay. So register pack. Let us see whether it is available or not. Yes, RS pack 8, right? So we can add that one. We also will need, what else we can need? We need some registers. So simple register. Okay. So we can see it is generic register symbol. So we'll be using that. But in actual hardware, you can use different other registers which is available to our lab. So we can double click on it. Then we need some capacitor. Okay. So capacitor, generic non-electrolytic would be good. Apart from that, we need op-amp, right? So say LF351 op-amp. So LF351 So we need to connect number of connections. We can also go with 47, right? So we can do that one. And okay, so let us start with this hardware. So what we can do, we can place this. Now you can see that we can make a node here, okay? And then we can place a where label. And so let us give this VCC, okay? And so then we'll be bringing that capacitor here, and then we'll connect this. We can connect a again node here, and again we can place this. Now we want to connect it to VCC, so I'll be use the same label, and so it will be connected to VCC. So I do not have to connect it from means this the with wires, but if I name this way, it will be connected. Okay. So similarly, you can do it for your XTEL1, XTEL2 with crystal oscillator. So if you go for the library, you can get it. And then we want that P1 will be using. So this P1, T2 is the clock. So we'll be creating a node here, and then we'll place that as AD clock, CLK, right? And then we want that P1.2 and P1.3 can be used for the ALE and SC of ADC, right? So we'll be again placing that one, ADC ALE, right? So P1.2 is the ADC ALE, and P1.3 would be ADC SC, okay? Now what we want, our EOC should be connected to one of the external interrupt, right? And so what we do, and we have told earlier that this EOC is basically a low signal during the conversion. And so it will generate a rising edge after the conversion. But this external interrupt is configurable with falling edge. And therefore, we need to use an inverter. Okay, so NOT gate. So that NOT gate we can use. And so we can use that. Now we are doing just mirror image so that we can get this one. So we can connect this one, and this one we can create a node again, right? And we'll be giving this as ADC EOC. Is that understood? Okay. Now we can go for ADC. Now you can see that input channel is here, and the output, digital output, which should be connected to microcontroller there. So we can again go for mirroring, and then sorry, we can connect this way. Now you can see this is P0 and out one is also. So we have to check this ADC. Out one pin number 21 or 17, which one is LSP and which one is MSP, right? So let us see from our Otherwise, we have to. No, I have not given here. So let us open. You can see it from the data sheet, right? So yeah, yeah. So 17, you find 17 is the LSB and 21 is the MSB. Okay. Okay. So if I connect 21 into this, it will not work, right? So what is needed, that we need to connect these to MSB P7 and then there will be a crisscross. So this is a means the means circuit will be clumsy. So what we can do, we can go for bus and then we can draw like this. Okay. And then we'll be just connecting this. Similarly, so we have connected. Now our connections must be named the way we have do it for that. So this out one was MSB, right? So we can place the where like AD, say O, sorry, O, this is MSB 7, ADO 7. So we have written ADO 7. So this should be ADO 7. Okay, so the same name should be there, ADO 7. And similarly, we'll be giving the name of all these pins like that. This is 6. This is 6, then 5. Okay, then 4. I think I have missed it, so we can uh, edit the level. So that would be 3. And I have to go for this, let AD4. Then I have to go for, no, I have missed somewhere. 7, 6, 5, 4, 3. Okay, this one. 2, then 1, then 0, right? So similarly, we have to come here and place this as 6, this as 5, this is 4, 3, 2, then 1, then 0. Okay. So what we have done, we have avoided that crisscrossing of this wire, and then we have just connected this way, right? Then we have to connect this. So we will create this, then EOC, then we need also this OE, right? we need this V reference and then ALE. So we can directly use the name of that, right? So we can see that ADCCLK, so that should be connected to there. Sorry. So ADCCLK, then ADCSC, then ADCEOC. Okay, so then it is going to connect this, right? Acha. Then ADCALE, ADCALE. Then OE, we want to connect it to permanently VCC. So we can place this and then we write V small cc, right? So it will be connected there. V reference plus also should be connected to VCC. And then we need to create a ground. Okay. So we can get it from these terminal modes. And then we can have ground. So we can place here. And then we can connect it here. Okay. Is that clear up to this? Right. Okay. We need source and we'll be working with sinusoidal source. So we can connect that. And then we are connecting it to channel 0. So it means that this ADC must be selected. So we are doing here fixed addressing. So that means other channels cannot be selected. Otherwise, we have to connect these from the microcontroller, these connections. So here we are we are connecting these to single one, and then we are labeling this as ground, small GND, just to avoid. And then we will name this as also small GND. Okay, so this means that it is connected to here. Okay, so our ADC input is ready, output is ready, OE is activated. We have to code for these signals. So from ADC end, it is okay. Now we have to work with DAC, right? So we want to connect this DAC onto P2 port, right? So we can go again this one. We'll see that DAC is available here. And so we can place here, right? And what we need, we want to have this. So we can go for again bus concept, right? So we can connect. Okay. And so we'll be directly connecting this. Just we have done, and then we have to label it. So let us do this and work with these only. So that we can learn the complete work from the scratch. Now, once again, you have to see that which one is the low bit, right? So let us go. Yeah. So you can see from here, A1 is the MSB and A8 is the LSB. Okay. So A1 is the MSB. So we can place like DA input, DAI, and that is MSB. So 7, right? Now we can just do this 6, 5, 4, then 3, then 2, 1, 0. So this side is done. And so we have to work in this side. So this is your 7, 6 like that. So we have to place this. So this is to be connected with 0. Okay. Then 1, then 2, then 3, four, 5, 6, and 7. Okay. So we have connected the input end of the DAC, right? Now, what is the recommendation for DAC? Other output. So we'll be just doing this. And then we need some registers here. So we want, yeah, so we'll be going there. So find the resistance. And the value should be changed. Then this 15 will also have through resistance. Now, what about this compensation and VEE? So, sorry, you can see. So, we can, yeah. So we have 5K at the 15 and then grounded, 5K and then V reference. So we'll be connecting to 5 volt only. 16 is connected a 0.1 microfarad capacitor to minus 15 volt. Okay. And 3 is directly connected. So we can use that configuration there. So we need a capacitor, right? And then we can connect this. We can also connect this. We can change this value to 0.1 microfarad UF. Okay. And then we need to connect it to the ground. So we have this ground GND. So we can create, and then we can label this GND. Okay. So we can connect this. Now this is connected to again GND, right? GND. And this is connected to VCC. Okay. Now we have to change the value to 5K. So this value we have already discussed earlier, that how we can decide this value, right? So that depends upon that the op-amp based circuit will be using. So 347. And we'll be just flipping this Y mirror to have this as ground, right? Okay. Now we need a source of DC, two sources of DC. One is plus 15 and one is minus 15, right? So we can place here, and we can place another here. We can connect to there and there. Now you need to check that what should be the connections 11 and 4, pin number 11 and 4. Let us see if it is available in our, no, it is not available because they have used this. So we can go to there and we can find. So 4 is connected to 15 volt and 11 is connected to minus 15 volt. So we have 15 volt. So it is minus 15 volt. Okay. And then we need a resistance which will be connected here and then here. We can bring this here. Okay. And then so now we can name this. Have we named it? No. So we can name it DAOP. Right? So we'll be naming this DAOP. And then we'll change this resistance to 5K. Right? And then we'll again, so this is DAOP voltage V. And this should be connected to ground GND. Is that clear to you?
Yes, sir.
Okay. Now you also want to check it through oscilloscope. So we'll place it here, say, and again we can keep this here. So we can do different way. So we'll be doing here. So this terminal, this is AD input, ADIP. Okay. Okay. So in channel A, we are giving ADIP, and in channel B, we are giving DAOPV, the output of the op amp, right? So we should be able to see that. Now we need to set this one. So if you observe that we have this offset, offset of 2.5 volt and amplitude of 2.5 volt, and frequency can be arbitrarily set, so that our peak to peak value does not cross 5 volt, and say this is 50 hertz. Okay. So I hope that our hardware is complete now. Okay. So we want to see that, yeah, okay, for the time being, we have not coded anything here. So let us rebuild once whatever is available, build this project, and then just check. This is, we can change it 11.059 so that it will work with the whatever we have done. And then let me see. So this is the debug X today. Yeah. So okay. And then if I run, so we can change this time. Okay. And then we can change the magnitude, right? So this is our input, which ADIP is connected to channel A. This is coming. Okay. Now we want to write the output and get the signal. All right. So reset vector start. What we need timer 2 and the external interrupt 0. We have connected there, right? So this EOC is connected to external interrupt 1, not 0, sorry. So 1 is connected. So tell me that what are those addresses for timer 2 and the interrupt 1, external interrupt. Find it and tell me. Okay, Aishman, what is that address? Hmm? No interaction from student side. You have to remember it very quickly, no? So interrupt 1 is 13 and timer 2 is 2B. So 0013 hex for external interrupt 1. And then we can use SJMP. What we want in the external reading, ADC read. Okay. And then ORG 002B hex. So this is for generating clock for ADC, right? And SJMP ADC clock. Okay, so we have this one. This is not needed, so we can directly exclude that. Right. So what we have to do, we have to configure that initial phase. So for the timer 2. So we'll take one by one at a time. So first we want to configure the timer 2. So for that, we'll go to that circuit and try to understand that what will be the relation between the frequency and that programmable output clock. Right? So here we have observed clock frequency FOSC is oscillator frequency. So directly whatever we are giving that one, and then RCAP 2H, RCAP 2L content. So what we want that this frequency should be 640 kilohertz. This is 11.059 megahertz. So you give me this value in hex. Anshuman,
Yes, sir.
you calculate and tell me. What happened?
FFFC.
This R cap 2H and 2L? Okay. So I'm completely relying on you. And
So that was
so
640
tell.
kilowatt. This was
Yes.
640 kilowatt. Yeah,
Yes.
then
So what we have to do, move R cap to H, comma, hash. Now the first one should be 0, huh? FFX. And then move R cap to L, comma, hash 0 FC X. Now you can write here that the content R cap content for generating the 640 kilohertz, sorry, in programmable clock out mode. So we need to select that mode, right? So we can see from here that we have to enable this T mod 1, T2 mod 1, right? Then C2 bar should be 0. Then this will be activated, right? And this will be activated. So this part will be off. And then we have to start this tier 2 bit. R cap 2 and LH is done. We have to, so we have to see that what is that T2 mod, right? So we have T2 con. So there we will be using these bits. So reloading mode we need, right? So this would be that 0. T2 bar will not be doing this way. Okay, so we'll be separately doing this. And then timer to mod, T2 mod, DCN is 0 and T2 OE is 1. That means 2, 0, 2, right? So we can use move T2 mod and what we want to store 0, 2 hex. So programmable clock out and up counter, right? Then we want that CLR clear bit. I think clear is there. Okay, let me see. Clear bit, which bit? T2 con dot 0. So that means it will count on 16-bit auto reload. Right. If you have any question, you can raise immediately. So T2 con bits. So these bits are flags. And what about this RLK, CLK? the circuit, in that circuit it is not affecting. Tier 2 will be setting separately. This T2 bar should be sent, so it should be again clear. So these 2 bits should be cleared, right? CLR T2 con dot 1. So this is required to set it in timer mode. Okay. And then is that our timer 2 configuration is over, so then we can start. So set B T2 con or tier 2, just we can write here. Let us see. And then we'll be writing for the time being this ADC read with level, and then we'll be doing return I. And not doing anything at this moment. But for ADC clock, we need to write something. Is it required? Because I think this is not required. Let me see, then we'll be discussing. What is required, that starting these and our connections wise, this is the circuit, so it will get this path through this one divided, so directly it will do. So no interrupt is needed. Okay, so ADC read is done. So let me see that clock is working or not. So how can I do that one? So I can connect that ADC, and we can connect ADC clock CLK, I think. Sorry. ADC CLK. So this pin I should get there. So let us build. No errors. It is compiled successfully. So now we should be able to see at the C1. So if we go for this, C means this one, right? And so let us do this timing. No, some problem is there. Let us check. T2 bar is 0. Tier 2 we have set it. This T2 mod 1, T2 OE, that should be 1. And then it should generate. Let's see this T2 mode. T2 OE. Output enable bit. That's fine. Okay, let us see this one. Okay, did I use the same one? ADCLK. Oh, I think that we have missed. ADCLK. Okay. Yeah. So you can see so we are getting that T2 here, right? So we are getting the output and ADC is getting that clock. Is it clear to you? So what we are doing that we are configuring it as in 16-bit auto reload mode, and then we are just following this circuit. Okay. Now this T2 part is over, right? And let us disconnect this clock for the time being. And just to see that this signal. So we need to read that one. So for that, so this part is for configuring the timer clock one, right? Okay. And what about this P2 and P3 or P0, right? So we have done something here which is actually required some connection. So that pull up register, because this P0 is not internally pulled up. So we can do this. Okay, I wanted to have this bus. Okay, let me do this. Okay, so we can just connect this ADO0 to something. So we can name it like this. ADO0. One, two, three, four, five, six, and seven. So it, and then this part, you can write that VCC. Okay, so this type of component is also available in the market. So which is actually pull-up registers for us, right? So I think we have to delete the 1 second. ADCLK. What is the name for ADCLE, ADCSC, and ADCOC? ADCSC and ADCEOC, right? Okay. Okay. So and then Okay, is that clear? Are we and need any change? Okay. Okay. So our circuit, I think now it is correct. Yeah. ADIP. So we can observe that ADC clock is working here. And then ADIP and this one, right? Okay, so ADIP, anything changes happened? No. Okay. Then why it is not coming? Let me save. Build it once again. Run it. Okay, so we have changed this. Yeah. Okay, so we want this to be coded. So what is needed? We need to open this interrupt, right? So move IE and then what should be the content? So let us go and recheck ET2, ET1, ET0. So this should be 1, right? Or do we need this? We do not need this because we are not working with the interrupt. So I content EA, this one should be, and then external one. So it means that we have 8 and then 8, right? So 88 hex. So enable external interrupt 1 for ADC EOC. Okay. So that means we are allowing, now it will come here, right? So we have written that part here. Okay. So we have to set this in falling edge, IE content. Now P2 and P0 should be input and output. So P0 is the input, right? So move P0 input, so FF hex and move P2 as output 00 hex. And then, so what I am not doing, I am not using that one, but you can use this, right? So like this INT edge is TCON bit 0, right? So let us, okay, so I can show you this one and ALESC will be doing, okay. That is set be INT 0 edge. So let us use that one. INT1 edge, right? Equal EQ then we have this T2 con or okay, so what I was telling, Tcon dot 0. Dot 0. Is it for int 1? We have to check, huh? So IT1 in Tcon register is at this one, right? So external interrupt 1 trigger type. So IT1. So that means it is 0, 1, 2, right? So Tcon dot 2. And so we have to set that. Set B that, sorry. int1 dot, sorry, underscore h. Okay, so this is done. Apart from that, we have that we want to set this ALE, okay, then SC, then EOC. And this is also equal. And we have to go as per our connection. So P1.3 is the SC, P1.2 is the ALE, right? So ALE is P1.2, SC is P1. And EOC is P3.3. PKU P3.3. Is that clear to you? And then whatever code we have written here, that can be utilized, right? So we have to set this one. So this structure, set BALE, set BSC, clear ALE, clear SC, right? So that is for first one. So we'll be doing after that clock is set. Okay. So we'll be doing start ADC conversion. So we'll be doing set B ALE, then set B SC, then clear ALE, and then clear SC. So this is for first sample. Okay. Now, while we are coming at this location. So we can go this push ACC, then push PSW. Done. Then before return, we have to go for, sorry. Pop PSW, then pop ACC. And within that, so that conversion is over. So we want to read, move into A, okay, from P0. So we can also use the macros there. So here we are doing, so read digital value for sample, and then you move the same content as we are going for pass-through example. So we'll be moving this content to P2 where that DAC is connected, the same one. So pass it to DAC. From ADC you read and pass it, right? So we can check this one happened. Now we need to initiate the start conversion for next sample. Okay, so we can go for initiate conversion for next samples. And so we have to copy paste this part and do this. Is that clear to you?
Yes, sir.
Okay, so this is not required for us. Now we need to check whether our syntaxes are wrong or right. So build it. Some errors are given, so let us check what are those errors. Some syntax which is telling that possibly that error may be in these. So let me check. So whether we need this one or not. Yes, so this colon is not necessary here. Okay. And so now no error. It is built and we want to see that one, right? So we have B. So let us stop. AD clock, AD ALE. Yeah. Clock is working, but start conversion is not working. Okay. Okay. So what we can do, it means that this equal is not working properly. So we can get it from the examples about this one. So let us directly use that particular one and then check whether it is working. Then we can solve for that part. Okay. So L is P 1.2. P 1.2. S is P 1.3. So then P 1.2, 1.3. And the same code we have to set here. This is one. Not only that, this int content. So that also tcon2, tcon.2. So we'll be fixing this later. So let us check whether it is working or not. Yeah. And then let us run. So still it is not working, right? So we need to debug. So this should also blink actually whenever this is getting digitized, right? Okay. So where is the problem? Let us lock it first. Then do this. Now we have set this 88 IE, right? So you need to check whether that was correct or not. IE. So we want 81. So 0, 81 is this one. Yes, this is 1, 0, 0, 0, 8, and this is 8. Okay. This address external interrupt 1 we have set, right? Anything else? P0 is reading. ATCAD.
Sir, route 8 is not written ADO 0.
Which one? Oh,
Out 8.
out 8. Yes, yes, yes. Okay. ADO 0, 1, 2, 3, 4, 5, 7. Here also ADO 0 to 7. Okay. Anything else you check in the hardware? Okay, let us run this once again. But there should be a blink in the SC and EOC. right? So let us connect that SC, ADC SC, ADC SC, ADC LK, ADC LK. No. So ADCSC is not working. P1.2 ALE and P1.3 is the ADCSC. Right. DAC, did we connect properly? DAC 16 and 3 should be connected to minus 15 volt. So this should be edited. And so I can connect it instead. Okay. So V reference and other things. So it means that once it is set and reset, that pulse is created, then it is not coming here.
Sir, for enable interrupt 1, we have to send IE as 84 hex.
84
Yes, sir.
IT1. Okay, so that's that content you should check. Okay, let me see. Yeah, very good. Right. 84. So that was the problem, right? So what is needed? That B. Now we are finding something is clipping, getting clipped, right? So let us see where is the problem then. So now we are having that SC, correct? Okay, that is good that you have identified the problem and got the solution. Now we have these. So instead of this VCC, if I connect it to 10 volt, what will happen? What should I get? Still clipping is happening. Okay. So why that clipping is happening? Okay, one thing we do, let us change this amplitude to 1, 1. Yeah, so that amplitude is getting crossed, that's why. Right? So it is working with this, right? And we get this amplitude. Okay, so I think we need to check that. Yes, I missed it, ET1. It should be EX1, right? Okay, so now is it clear to you?
Yes, sir.
And now similarly, what we can do, we can add with this program. Let me see whether we have that. This one. Virtual terminal. Okay. So this virtual terminal can be added here. And then you can connect this RxD TXD with TXD RxD of this, right? And then whatever value you are getting from ADC, which is available in the hex, you can convert it into BCD and then send that into this terminal. Okay. And so I think if you double click here, you can set the baud rate, the bit patterns or so. So whatever your UART protocol is working with, so that you can set. Okay. And then if you go to the properties, so somewhere you can see that property would be that not here, but while writing, you can mute the echo on or off, and then accordingly. So you can connect this one and you can use the interrupt, which is available in the 230023 location, right? So with this example, we have seen that how ADC is working. We also learned that how we can make our circuit neatly. And then we learned how interrupts are working, how the timer 2 can be used to generate the clock of the ADC. So we do not need external circuits for clocking. We can do it using that, but T2 will be used. So that is one disadvantage, that T2 will be busy for that purpose. But otherwise, if T2 is necessary for your project becomes big and it is necessary, then you can have a separate clock source for ADC and then T2 can be released. Okay, so if you have any question, you can raise. And so my suggestion is to complete this serial communication one. So what you have to do, you have to get this data and transmit this data into this virtual terminal. So on this screen, that particular data in BCD format will be displayed. Okay. So you have to practice that.
So we don't have to send data to DSC anymore.
DSC, after DSC, DSC is will be there, but apart from that, you can also see. So what does it mean? It means that this device is the local region. Say you are placing this device at the say some furnace controller or so, that site. But at the same time, you want to know what is this input signal, this measured value, right? And so from the control room, which is far apart from your place, this local means the local region. So this DAC will work with the control mechanism or control circuit, which is analog in nature, for example. So your analog controller will be controlled by this DAC output locally, and you want to see, observe from the control room, what is this measured value of this input signal. This can come from a sensor, right? The input to the ADC. Okay. So this will be there. At the same time, this virtual terminal will also be there. And thus, we are also experiencing the multitask system, isn't it? So we are generating the clock using the timer 2. We are reading the ADC. We are writing it into the DAC. And then we are writing it into the virtual terminal. Is it clear to you? And the simulator can help you to understand this very concretely, right? So you have, all of you have understood, I hope, that what should be the practice, how we should practice, and what should be your answer. So it should be complete structured so that anyone can take it and reproduce it. So mute yourself, whoever is unmuted. Any question?
Sir, so for
Hmm.
sending it in the serial mode, we will send the data in the main. Like in the main loop, we will be sending it, and in interrupt, we will be reading it from the ADC.
No, this main will not change actually. You are reading the data here, okay? You got my point? And then you will initiate that transmission of that data. So DAC will be there. After that, you have to put your code. Okay. But when you are putting this code, right? So you will get there, means if you use the interrupt one, so you can write say org 0023 hex, right? And then you want to go for SJMP that AD transmit. Okay, and then you can write your data here. Sorry. So for the time being, I am keeping this written. Right. So you are transmitting the data. So during that period, this will be used, this interrupt will be used. And once that data is transmitted, then you go for next sampling. So it will be in a sequence. Understood? So we do not need to put that code in the main routine. We can put if we are going for that flag checking, right? Is it understood? And another point, you need to check this. What is the syntax here for this? Whether it is EQ or equal. Equal probably not. Or reg. So I think I may find it with my, no, not here. Let's see if it is there. No, not this one. Okay, so we have to see from other examples. So which is given by this Proteus itself. So you can go there and see that one. Or else I will let you know later if you don't want to do that. Okay, any question? Okay, so you keep your Proteus ready during the examination. So I may give some simulation problem also. And then you need to upload the screenshot of your work. Okay. And obviously the circuits or the code must not match except this microcontroller. So the pattern or the way you are connecting your circuit that may not match and should not match with your friend's one. If I see that, it will be completely zero for both of them, who is helping to copy and who is copying. And don't ask me that why you have cut your marks, please increase my grade. Don't ask me that time. Okay. And don't tell me during that examination that, sir, my Proteus is not working. So I am telling you in advance. So keep your things ready. Is that clear to you, Anshuman?
Yes, sir.
Okay.
So what will be the exam pattern?
Is similar to mid-sem, but now I am thinking to include this simulation also. Okay. And your online examination is for 2 hours, right?
Yes, sir.
So the question will be of 50 marks. Out of that, we'll have similar to that 15 for MCQ, 15 or less. And then remaining will be for subjective question, pen and paper, and simulation. But I should not see anything. This means same content in every paper. So it means that you need to understand what you are writing. Okay. Anshuman, sorry, Ayushman, you are telling something? Anyone else have any question?